Good afternoon, all of you. Thank you for watching this video. My name is Jesus Toledo, and I will present the paper that we have written with John Sin, Hector, and Jan. The title of this paper is Passive Observer for Distributed port-Hamiltonian System. I will give you a brief background, then I will present these two observer design, then an example, and at the end some conclusion. Boundary control port-Hamiltonian system are systems governed by PDEs with actuation and sensing at the boundaries, the spatial boundary. In here we have a state variable x that depends on the space and the time. We have a matrix P1, we have the space derivative, we have H, another matrix that can depend on the space also. We have again the state variable, and we usually call this effort variable, Hx, we call it effort variable. Then we have another matrix P0, and again the effort variables. The boundary conditions are a linear combination of these effort variables. You can see here that we define boundary for variable F and E that depends only on the PDE structure, and the effort variable evaluated at the boundaries. So here we have an input that we can impose to this system. We can define an output that we usually call it conjugated output, which means that this output multiplied by the input are power conjugated, meaning that the multiplication it's power. And in this case, for the observer design, we will consider that we can measure this y or a part of this, and this will be characterized by this matrix C. For example, we have the wave equation, which can be represented by this PDE with velocity at the left equal to 0, for example, and the force at the right equal to some function that we can decide. The same system we can represent it as a port-Hamiltonian with the matrix P1, P0, and H matrix. If we design these state variables, which we call it the strain and the momenta, they are energy variables, then we can compute these boundary port variables, which are linear combination of the effort variable evaluated at the boundaries, and then we can characterize it or input through this matrix and the output to the other one. So in this case, we have the input, it's the velocity at the left and the force at the right. And the output, you can see that they are conjugated. And in fact, if we multiply U by Y, it's the H dot, the H is the Hamiltonian, the total energy storage by this string, and U by Y, it's the power coming in or coming out of the system. So at the end, we have a PDE like this, and the boundary condition that we can impose in here, and we have the conjugated output. So in this case, we are going to design an observer for this kind of system, where we can measure this conjugated output Y, or a part of this characterized by this matrix C, or even when we can measure not energy variable, but another variable, for example, in here, the displacement, which it does not appear in explicit on the energy variables, but we can also design observer in that scenario. So for just to prove existence of solution, there is a theorem that this boundary condition are the good one. So we have to prove that WB, the matrix WB, has full rank and satisfy this condition, this inequality. So when we satisfy this, we have a boundary control system, meaning that we have existence of solution, and we have we can put some different kind of input, some function in here. And when this function is equal to 0, then we have a contraction semigroup. So now we are gonna design the observer, which is, it has the same structure as the real system. You can see exactly the same PDE, the same boundary condition, but new variables. And I call it all of them hat, X hat, U hat, Y hat. So we have to design this U hat in order to make this system converge to the real system. And that is the same problem of prove that the error between these two systems converges to 0. So we define the error as the real system minus the estimated one, and we get the same structure as before. So the first, the simplest way to design these observers is when we can measure the conjugated output. So in this scenario, we have Ym proportional to the conjugated output. So, and characterized by this matrix C. Then U tilde is equivalent to minus L Cy tilde, which we usually call it output feedback. There is no external dynamic in here. So then we have the error system, and this error system has a new matrix of UL, and these are the boundary condition of the system, and they are fixed to 0. So as before, we have to prove that this it's a good boundary condition and converge to 0. So for that, we have this theorem where we only have one condition, that WL is full rank and satisfy this inequality, or equivalent that L is positive. So we implement this in an example. So this is the full sensing. So we are in the string, we are measuring both boundary output, and we can design L as a diagonal, L1, L2, and it's at the end we only need to have L1 positive and L2 positive. So we do the simplest design, L equal to identity. We simulate a real system with 200 state variable, and also we simulate an observer for this system, because we are proving the stability always for the real system. So the observer with this size, it's the one we can prove it. But to be more realistic on the real implementation, we design also the same observer for a reduced order system of 50 state variable. The time is between 0 and 3, and in this case, we are sensing force at the left and velocity at the right. We use an structure preserving method for the discretization given by Trenchant. So here we have an initial condition, and the wave, the string will move always. There is no dissipation, there is no control, so it will move a long time. We set an initial condition 0 for the observer, and it's converged to the real one. Here you can see the error, this minus this, converts to 0. And even a reduced order observer will converge to the real system. Here also we have the simulation in a video, exactly the same, but in a video where we are measuring the strain here and the velocity at the other side. This is the initial condition for the displacement and the initial condition for the reduced order observer. And we can see that the observer also converge. There is another corollary also from Villegas that can prove the exponential convergence. And we only have to prove that the effort variable, the norm of the effort variable, match one of these two conditions. The norm of the effort variable at the right or at the left. This A is at the left side and B is the right side. So we have to prove one of these conditions and we have exponential stability. So we did it for a partial sensing. So in this case, we are only measuring the strain at one side, only one sensor now. And we can develop everything, and we need L now it's a vector column, a column vector. And we need L2 equal to 0 for proving the existence of solution, and then we can design L1. We check this condition, and at the end we match one of these, the condition of the corollary. We do also the simulation, and we have L design, the simplest design. And again, the same problem before, but now we are only sensing the strain at one side. And you can see that it's quite similar as before, but now it takes more time to converge to 0 because we only have one sensor. And this is the video, exactly the same. Now we are only measuring at this side, and it takes a bit more, but we are proving exponential stability. So now what happens when we cannot measure output, the conjugated output, and we can measure displacement, for example, in the string equation? We have to add some external dynamic to the system, to the error system. And then we can prove that the error system can converge to 0 asymptotically or exponentially. We have some observers that people use in the literature, and they have different way to prove the convergence. But now we are trying to generalize everything in this framework where all that kind of observer, we can prove that they are nothing but the passive interconnection between the Euro system and an external dynamic port-Hamiltonian system. So we have the interconnection between two port-Hamiltonian systems, which remains Hamiltonian and remains passive. So we are proving everything in this way. So we have a proposition from Mike Kelly in order to prove that we have a boundary control system. This interconnected system is a boundary control system, so we have existence of solution. Then we have another theorem from Villegas that says that the interconnection of an infinite dimensional system and a finite dimensional system converge asymptotically to 0 if this block C is a strictly positive real. So we have to prove that only that this block is strictly positive real. And then we have this lemma with the condition for the strictly positive reals, but only I want to do the remark that for the port-Hamiltonian representation, we only need to have RC greater than 0, RC positive definite, and then the block C, it's a strictly positive real. Then we can implement it in some examples where we can measure the displacement at one side. And for example, here we have exactly the same problem as before, but now we can act on the velocity and the force at the other side. It's free, the string. The following observer estimate asymptotically the state variable. So here you can see the observer, the only information that it takes is from the input, the function, the actuation, and W, what we can measure, but all the rest it's known from the system. And we have an external dynamic, this theta, and this was an observer that they used in Google 2009, and they proved also the asymptotic stability. But in this case, we proved that the error PDE, this one minus this one, it's nothing more than the interconnection between two systems, and it's passive, and we have a strictly positive real system here, and then we have asymptotic stability. It's another way to deal with this problem. We do the design, this exactly the same, but now we measure only the displacement at the right side, and we have more time because now it takes more time to converge. We use the same discretization method. Exactly the same initial condition, it moves along time, and the observer in the same space with the same size of these converge asymptotically. You can see the error here, and even a reduced order observer will converge. Again, the simulation, we have only the displacement sensing, and we simulate a reduced order system only to be more realistic. And okay. Then we have another proposition where we can prove the exponential convergence. In this, it's more difficult to prove it, but we have the condition that the total energy, meaning the energy of the error system plus the energy of the external dynamic, match one of these two conditions, then we have exponential stability. And it's all. We have only to prove one of these two. And again, a new example where we are measuring, in this case, we are measuring T0. There is a mistake here. So the observer estimates exponentially the state variable, and here we have the sensing, it's the force at the left, and it's clamped also at the left, and we can act on the right side and the other side. So here there is a mistake, and we're measuring this. This also was a work done by Guo 2007, a very interesting work where they design an observer with information in one side by the act on the other side. It's called a non-collocated problem, and it's very hard to prove all the stability things, and this is something that we are working on to do in this framework, the port-Hamiltonian framework. But for now, we have that the observer, it's nothing but interconnection between two port-Hamiltonian systems. So if we rest this system minus this system, we obtain the error system like this with this boundary condition. And the boundary condition, you can see that here we have a part which is the conjugated output of this system, and we have a dynamic term. So it's quite similar to the result from Ramirez, where to prove the exponential stability, we need this term, this conjugated output of the system in here. We do the design also, And now we are measuring the force at the left side, and that it's the system move a long time, and the observed system converts to this one. You can see the arrow here, and the reduced order observer. So exactly the same simulation, but now we are measuring only the strain here. And more interesting problem that we are not dealing with in this paper, but it's something interesting, is that with the same observer, we can control the stream in a non-collocated way, meaning that we control the other side that we are measuring. We measure at 0, but we control in 1. And we do a damping injection in that side. And you can see that the wave equation, the string will converge to 0. So they did it in Google. So we have the strain measure, the force sensing at one side and acting to the other side. And the wave can go to 0. So for concluding, we are gonna do the same for another example, a bit more complex, where we have the Timoshenko beam, which can be represented in the port-Hamiltonian representation with P1 like this, P0, H, X, and here we have the state variable. And what are not the state variables is the transfer displacement and rotation angle of the filament. And we're considering that we can measure these variables. They are not energy variable, but we can measure, and we can prove also an observer we can design an observer for this system. So we define the boundary port variables, then we characterize with these matrices the input and output, and they are conjugated. So the following observer can estimate the real values asymptotically. So here you have the PDE. We have two boundary conditions that they are exactly the same as the real system. And we have the other two that they are given by this with two design parameters and with the sensing is WB and phi. It's the displacement at the right side and the angular displacement also at that side. And also we have two external dynamic of this system. And then we can prove that for an initial condition like this of the beam, it will move a long time always. And we can design a full order observer, an infinite dimensional one, and will converge. You can see that the error converges to 0, and even a reduced order beam observer can converge. And here you have the simulation where we are measuring the displacement at that side and the angle of the beam, the blue one, and the red one is the estimated one. So it was presented a class different observer for the class of boundary control for Hamiltonian system, and for every case we can have some condition for asymptotic or exponential convergence, and the ongoing work of my thesis is to use this observer for control purposes.